You know how your phone just magically unlocks when it sees your face? Or how Netflix seems to know exactly what movie you're in the mood for? Well, that's not magic. It's machine learning. And today, we're going to pull back the curtain and give you a straight-up, beginner-friendly guide to what it is and how it works. But to really get a handle on machine learning, we first have to talk about, well, learning itself. The AI pioneer Marvin Minsky said it best. Learning is making useful changes in our minds. It's all about adapting, getting better, and making sense of things through experience. It's what we humans do.
And that is the billion-dollar question, isn't it? How do we take this deeply human concept, making useful changes, and bottle it up, put it into code, and get a machine to do it? How do we build something that can actually improve on its own?
And let me tell you, the need for this is more urgent than ever. Why? Because we are literally drowning in data. Every click, every purchase, every sensor reading, it's a massive, endless flood. The data itself is cheap, but the actual knowledge, the wisdom hiding inside it, that's the expensive part. That's the gold. This is exactly why we need machines to learn. Some systems are just way too complicated for a person to sit down and write rules for. We need software that can change on the fly, adapting to what you do. And we need them to be like super-powered detectives, digging through that ocean of data to find the patterns we'd never see. So, okay, here's the textbook definition for you. Machine learning is all about programming computers to get better at a task by using examples or past experience. In plain English, instead of giving the computer a step-by-step recipe, we give it a goal, show it thousands of examples of what success looks like, and then let it figure out the recipe for itself. And don't think this is some sci-fi future. It is already here, and it is everywhere. I mean, just look at this list. Self-driving cars, the large language models we're all talking to, AI that helps doctors spot diseases, the recommendations you get when you shop online, even scientists using it to decode DNA. It's completely woven into our world. All right, so we've covered the what and the why. But now for the really cool part, the how. How does machine actually go from seeing a bunch of data to doing something smart? Well, it turns out there are three main ways we teach them. First up, you've got supervised learning. The easiest way to think about this is learning with a teacher, or maybe with a giant stack of flashcards. You give the machine tons of data that's already been labeled with the right answer. Thousands of pictures labeled cat, thousands labeled dog. The machine's job is to figure out the connection between the picture and the label. This is the workhorse of modern AI. Next is unsupervised learning. Now, the teacher leaves the room. You just give the machine a whole mess of unlabeled data and say, find the interesting patterns in here. It's like telling it to sort a giant pile of Lego bricks by shape and color without ever telling it what a brick is. It has to discover the structure all on its own. And the third major type is reinforcement learning. This is all about learning from trial and error, basically like training a puppy. The machine, or agent, tries to do something. If it does a good job, it gets a reward, like a digital treat. If it messes up, it gets a penalty. After millions and millions of tries, it learns the strategy that gets it the most treats. This is how AI learns to play games better than any human on Earth. Okay, I know those ideas can feel a little bit up in the clouds, so let's bring this down to earth and make it super concrete. We're going to walk through a simple, classic problem to see exactly how this stuff works in the real world. Okay, picture this. You're at a fish processing plant. There's a conveyor belt whizzing by with just two kinds of fish on it, salmon and sea bass. Your job is to build a machine that can automatically tell which is which. It's a straightforward problem. Salmon or sea bass. So how does a machine see a fish? It follows a simple three-step recipe. First, pre-processing. It just digitally isolates the fish from whatever's in the background. Second, and this is the most important part, feature extraction. The machine can't just look at the fish, so we have to tell it what to measure. We decide to measure its length and how light its scales are. Finally, step 3, classification. It takes those two numbers and makes a call, salmon or sea bass. But here's the thing. Almost immediately, you realize just measuring length isn't enough. Some salmon are small, some sea bass are big, and this little snag reveals the single biggest, most important challenge in all of machine learning. And that word is generalization. See, the goal is not to build a model that's a perfect student and just memorizes the training fish you showed it. The whole point is to build a model that learns the underlying patterns so well that it can correctly identify a fish it has never, ever seen before. That's the ballgame. That's the difference between memorizing and actually learning. This creates this constant balancing act. On one side, you have underfitting. That's where your model is just too simple. It completely misses the pattern. It fails on the fish it's seen, and it fails on new fish. On the total opposite end, you have overfitting. This is where the model is too complex. It doesn't just learn the general pattern, it memorizes the exact details of every single fish it trained on, including random noise. It gets an A+ on the training data, but fails miserably on any new fish. That sweet spot right there in the middle is the good fit. It captures the real pattern and ignores the noise. That's what we're always aiming for.
So we've gone from the big picture ideas to the nuts and bolts of sorting fish. But where is all of this heading? What's the end game for this relentless quest to find patterns in everything?
This whole idea of learning from patterns is the foundation for everything we call AI. But it's really important to know there are levels to this. Everything we have today, from our fish sorter to the most powerful language models, is what we call narrow AI. It can be superhuman at its one specific job, but it can't do anything else. The ultimate goal, the big dream of the field, is artificial general intelligence, or AGI. That's a machine that could learn, reason, and create across tons of different areas, just like a human can. And if we ever actually create a true AGI, well, that could trigger something straight out of science fiction, the singularity. This is the idea of a hypothetical point in time when that AI's intelligence starts improving itself, sparking this runaway chain reaction of technological growth that becomes so fast and so complex that it's just uncontrollable and impossible for us to predict. And that brings us full circle. We started this journey trying to teach a machine to find simple patterns in fish on a conveyor belt. But as these machines get better and better at finding patterns in everything, in financial markets, in our DNA, in our own behavior, we're left with this one huge, profound question. What happens when the student surpasses the master? What happens when their learning surpasses our own ability to even understand it?